Hello everyone. This presentation introduces my Assignment 2 project. I chose two symbolic music generation tasks using the Pop 909 arrangement dataset. The first task is unconditioned generation, where the model generates a standalone accompaniment sequence without a melody prompt. The second task is melody condition generation, where the melody comes from Pop 909 and the model generates a lower chord or accompaniment layer underneath it. I will organize the presentation around data and preprocessing, modeling, evaluation, related work, and conclusion. The overall goal is not to claim a production level music generator, but to build an end-to-end symbolic generation pipeline where every modeling and evaluation choice is explainable. This slide explicitly states the two selected tasks. Task 1 is symbolic unconditioned generation. The model samples a new accompaniment style sequence from learned Pop 909 accompaniment statistics. There is no external melody prompt in this task, so the output is judged mainly as a plausible symbolic accompaniment stream. Task 2 is symbolic condition generation. The melody is fixed as input prompt, and the model generates a lower accompaniment layer. The playback distinction matters. In the condition MIDI file, the upper piano track is the original Pop 909 melody prompt. The generated material is a lower accompaniment track, which may appear as strings or another instrument in GarageBand. So when I play that file, I'm demonstrating how the generated accompaniment behaves under a real melody, not claiming that the upper melody was produced by the model. So this slide maps the presentation directly to the assignment rubric. I will first explain the data context and preprocessing choices, then discuss modeling for both tasks, then evaluate both tasks with baseline and code-level metrics. After that, I will discuss related work and finish with the conclusion. Modeling and evaluation are separate sections, but each section covers both selected tasks. I also include several code walkthrough slides because the main technical work in this project is the conversion from raw MIDI messages into symbolic tokens, probabilities, and generated MIDI files. The data context is Pop 909. It was built for pop song arrangement research and contains 909 MIDI arrangements. The most useful feature for this project is that the MIDI files have named tracks, especially melody and piano. This gives a clean setup for both tasks. For unconditioned generation, I can model accompaniment events directly. For conditioned generation, I can use the melody track as a prompt and learn accompaniment patterns from the accompaniment track. I chose Pop 909 instead of an arbitrary MIDI collection because the track labels reduce ambiguity. I do not have to guess which notes are melody and which notes are accompaniment. That makes the task definition easier to defend and makes the evaluation more consistent. This slide clarifies the track roles because this can otherwise be confusing during playback. Melody is the original melody prompt. In the conditioned demo, the melody is heard as the upper piano track. Pop 909 piano is used during training as a source of accompaniment labels. The generated part is not the upper piano melody. The generated part is the lower accompaniment layer, which is written to a separate MIDI track and may be played by a string instrument in GarageBand. In machine learning terms, melody is the conditioned input, meaning it is given to the model as context, while the accompaniment layer is the target output that the model is trained to predict. So this is the first code-level step in the project. MIDI files do not directly give a clean table of notes. They give time messages. So the parser has to walk through each track and keep a directory of active notes. A note-on message starts a note span, and the note-off message closes that span. The result is a list of note objects with pitch, start time, end time, and velocity. This step is important because every later stage, including quantization, chord grouping, melody conditioning, and MIDI rendering, depends on having accurate note spans. If this parser is wrong, the model may learn impossible durations or miss simultaneous notes. I also treat note on with velocity 0 as a note off because this is a common MIDI convention. This is a small implementation detail, but it matters for reading real MIDI files reliably. In the code walkthrough, I've emphasized that this parser is not a model yet. It is the data extraction layer that turns MIDI into examples the model can actually learn from. For exploratory analysis, I counted the main symbolic units used by the models. The dataset provides more than 300,000 melody notes and almost 1 million piano track notes used as accompaniment labels. After grouping simultaneous notes, there are more than 600,000 chord event tokens. The condition task has almost 300,000 melody-aligned examples. These counts justify using simple count-based models as transparent baselines, while also showing why exact accompaniment predictions is difficult. The target space is large and diverse. The statistics also reveal a trade-off. There is enough data to estimate frequent local patterns, but not enough to memorize all possible melody and accompaniment combination, especially when rhythm, pitch, and chord voicing are included. This tokenization is one of the key design choices. A chord event is represented by its root pitch, the intervals about that root, and its duration in the 16 note steps. For example, root 60 with intervals 0, 4, and 7 corresponds to a C major chord shape. This representation is more compact than modeling every note independently, but it still preserves pitch, harmony, and rhythm. During generation, I smooth the register by keeping sample roots near the previous root, which reduces sudden octave jumps. The presentation is not perfect. It loses some expressive timing and velocity detail, but for this assignment, it creates a clean symbolic vocabulary that can be counted, sampled, evaluated, and rendered back into MIDI. This slide walks through the pre-processing code more carefully. The model should not depend on raw MIDI tick values because different files can have different timing details. I first convert note start times and durations into a 16-note grid. Then I group notes that starts at the same quantized step. If 3 notes start together, they become one chord event rather than 3 unrelated single notes. Finally, I convert the group into a token with a root pitch, interval shape, and duration. This token is what the Markov model actually learns. Quantization is a modeling assumption. It makes the data easier to compare across songs, but it also removes micro-timing. I choose 16 notes because it is detailed enough for many pop accompaniment rhythms while keeping the vocabulary manageable. I would also point out that grouping notes by starting steps is what lets the model represent chords instead of treating harmony as a random sequence of individual pitches. This is a modeling context for both selected tasks. Task 1 is an unconditioned next event problem over accompaniment tokens. The model predicts the next token from recent token history. Task 2 is a condition generation problem. The model sees the original melody, pitch class, bar position, and previous accompaniment signature, then predicts the lower accompaniment signature. In both cases, the optimized objective is likelihood on held-out symbolic events, and I report this as perplexity. I chose count-based backoff models because they are transparent and efficient. Even though they do not capture long-range form as well as neural models, a neural sequence model could learn richer patterns, but it would also require more tuning and it would be harder to explain within a short assignment presentation. So for task 1, the model is a variable order Markov chain over accompaniment tokens. Here, history means the last few accompaniment tokens that have already appeared. The model first looks for the same last 3 token patterns in their training set and samples the next event from what follows that pattern. If that exact pattern was never observed, it falls back to the last 2 tokens, then the last 1 token, and finally the overall event distribution. This is why the model is called a backoff Markov chain. The code loop samples 1 token, appends it to the generated event list, and updates the history with the last 3 generated tokens. The temperature parameter controls randomness. Lower temperature makes the common events more likely, while higher temperature creates more variation, but can make the output less stable. So this is the code behind the backoff behavior. You can see it more carefully. The backoff version degrades gracefully, so it can keep generating and can compute likelihood for every held token. This also gives a good example of the complexity trade-off. The model is simple enough to implement with dictionaries and counters, but still stronger than a pure unigram or bigram baseline. For task 2, the model is conditioned on an original Pop 909 melody prompt. The main melody is not claimed as generated. The generated part is a lower accompaniment underneath it. The model predicts an accompaniment signature, which is a set of semitone distances from the melody note down to active accompaniment notes. The condition contains melody, pitch, class, bar position, and previous accompaniment signature. This adds harmonic context, but exact prediction is still difficult because many accompaniment patterns can fit the same melody. This task is closer to automatic accompaniment than free composition. The model is asked to respond to a melody that already exists, and the output should support that melody harmonically and rhythmically. This is a code that explains exactly what the condition model is predicting. For each melody note, I look for accompaniment notes that are active at the same time. Then I convert those accompaniment pitches into interval below the melody pitch. For example, if the melody note is C and the accompaniment contains notes below it, the target is represented as distances below that C. This is useful because the model can learn relative harmonic shapes rather than only memorizing absolute pitches. The condition includes the melody pitch class, the position inside the bar, and the previous accompaniment signature. When explaining this slide, I would be explicit that the target label is the generated accompaniment signature, not the melody itself. So the melody is used to form the condition. Before showing results, this slide defines what evaluation means for this task. The main objective metric is held-out perplexity. Lower perplexity means the model assigns higher probability to real held-out Pop 909 accompaniment events. However, this metric is not the same as subjective quality. A model can have better perplexity and still produce music that sounds simple or repetitive. For that reason, I also discussed whether the outputs are valid MIDI and whether they are locally plausible under the melody. The baselines are unigram and bigram models for task 1 and a global accompaniment signature baseline for task 2. The point of these baselines is to make sure the model is beating something simple, not just producing files that happen to be playable. This slide shows the evaluation protocol as code. I won't go to details, but you can see. This slide connects the code to the evaluation table. Every number in the result slice comes from this same log probability calculation. So these are the task 1 evaluation results. The unigram baseline has high perplexity because it ignores all context. The bigram models improve substantially, which shows that the previous accompaniment events already contains useful information. The 3-event backoff model performs best, with held-up perplexity of 132.46. This demonstrates that local event context helps explain real Pop 909 accompaniment events. The code computes this result by summing log probabilities on held-up events and exponentiating the negative average. The musical interpretation is that accompaniment has short-range structure. Once we know the reason chord shape and rhythm, the next event is much less random than a unigram model assumes. For task 2, the condition model improves held-up perplexity from 961.48 to 945.33 compared with the global accompaniment baselines. The improvement is modest, but it shows that melody, pitch class, and local context add some predictive information. Strict top 1 accuracy is low for both systems because accompaniment is not a single answer task. Many different lower chord patterns can sound reasonable under the same melody note. In the condition demo, the audible upper piano track is the original Pop 909 melody prompt, while the generated part is the lower accompaniment layer. This result also explains why the audio may not sound like a polished pop arrangement. The model is learning local accompaniment signatures, not global song form, tension and release, or human performance expression. This final code walkthrough explains what is actually heard in the generated MIDI files. For the unconditioned file, the generated accompaniment tokens are rendered directly as MIDI notes. For the conditioned files, I write the original Pop 909 melody notes to one track and the generated lower accompaniment to a separate track. For the related work, Pop 909 is a direct reference point because it was designed for pop song arrangement and provides separate track roles. The Maestro is a well-known symbolic piano dataset, and PDMX is relevant as a large-scale public domain symbolic dataset. Deep Batch and Coconet are examples of stronger generation systems that use more complex modeling and sampling. My project is intentionally simpler. It provides a transparent baseline that can be inspected through counts, probabilities, and held-out metrics. In that sense, the project is useful as a starting point. It defines the representation and evaluation protocol before moving to larger neural models. To conclude, this project completes 2 clearly defined symbolic generation tasks. Task 1 generates a standalone accompaniment style MIDI sequence without a melody prompt. Task 2 keeps an original Pop 909 melody as a prompt and generates the lower accompaniment layer underneath it. The results show that local context strongly improves unconditioned accompaniment likelihood, and melody conditioning modestly improves conditioned accompaniment perplexity. The main limitation is that these comp-based models are much better at local coherence than long-range musical form. Future work could add key normalization, phrase level recurrence, chord labels, or a small neural sequence model for comparison. The most important takeaway is that the project separates the melody from the generated accompaniment and evaluates the generated symbolic events with explicit baselines. So thank you. And I'll play the 2 pieces of music generated. So this one is task 1's music. and I'll play the second piece of music. Okay, so that's all for my presentation. Thank you.